we can get started with counting and probability. All right. Introduction to probability. Imagine tossing two coins and observing whether 0, 1, or 2 are heads are obtained. It would be natural to guess that each of these events occurs about 1/3 of the time, but in fact this is not the case. Table 911 shows actual data obtained from tossing 2 quarters 50 times. And it shows that it's approximately 25% of the time 2 heads, 25% of the time 0 heads, and 50% of the time is 1 head and 1 tails. So to formalize this analysis and extend it to more complex situations, we introduce the notion of random processes, sample space, event, and probability. To say that a process is random means that when it takes place, one outcome from some set of outcomes is sure to occur, but it is impossible to predict with certainty which outcome that will be. Randomness is not, it's common in nature, but not in computers. Random number generators use an algorithm to generate the numbers, so they're pseudo-random. But yeah, random stuff doesn't occur much in computers. For instance, if an ordinary person performs the experiment of tossing an ordinary coin into the air and allowing it to fall flat on the ground, it can be predicted with certainty that the coin will land either heads up or tails up. But it is not known for sure whether heads or tails will occur. The set of outcomes can be denoted as, the set notation from earlier this semester, heads or tails. Or it could be 1 or 0, true or false, what have you. We restricted this experiment to ordinary people because a skilled magician can toss a coin in a way that appears random but is not. And a physicist equipped with a first-rate measuring device may be able to analyze all the forces on the coin and correctly predict its landing position. Just a few of the many examples of random processes or experiments are choosing winners in state lotteries, selecting respondents in public opinion polls, and choosing subjects to receive treatments or serve as control in medical experiments. The last two are done by computers, so they're not completely random, but yeah. Let's see here. Let's see, the set of outcomes that can result from a random process or experiment is called the sample space. A sample space is a set of all possible outcomes of a random process or experiment. An event is a subset of a sample space. In the case where an experiment has finitely many outcomes and all outcomes are equally likely to occur, the probability of an event or set of outcomes is just the ratio of the number of outcomes in the event to the total number of outcomes. So the equally likely probability formula is just the number of outcomes in the in E and divided by the total number of outcomes in S. So there's one possible outcome from flipping a coin, and there's 2 possible outcomes, so it's 1 out of 2, or 50%, or 0.5 is the probability. For any finite set A, N of A denotes the number of elements in A. With this notation, the equally likely probability formula becomes the number of events divided by the number in the set equals the probability of an event. So n of E over n of S equals P of E. An ordinary deck of cards contains 52 cards, divided into 4 suits. The red suits are diamonds and hearts, black suits are clubs and spades. Each suit contains 13 cards of the following denominations. The cards J, Q, and K are called face cards. Mathematician Percy Diaconus, worked with David Aldous in 1986 and David Bayer in 1992 to showed that 7 shuffles are needed to thoroughly mix up the cards in an ordinary deck. In 2000, mathematicians used a somewhat different definition of thoroughly mix up to show that 6 shuffles will nearly always suffice. Imagine the cards in a deck have become by some method so thoroughly mixed up that if you were to spread them out face down and pick one at random, you are as likely to get any one card as any other. So, what is the sample space of outcomes? What is the event that the chosen card is a black face card? That would be 6 out of 52. Sample space would be 52, I believe. And the probability that a chosen card is a black face card would be 6 out of 52. So the event that the chosen card is a black face card would be 6. And the probability that a chosen card is a black face card would be 6 out of 52, or 6 over 52. So, sample space is 52, because that's how many cards there are. The outcomes in E are the Jack, Queen, and King of clubs and Jack, Queen, and King of spades. So the event would be 6. Now by part B, n equals 6. N of E is equal to 6, and according to the description of the situation, all 52 outcomes in the sample space are equally likely. Therefore, by the equally likely probability formula, the probability that the chosen card is a black face card is approximately 11.5%, or 0.115. Counting the elements of a list. All right. Some counting problems are as simple as counting the elements of a list. For instance, how many integers are there from 5 to 12? To answer this question, imagine going on the list of integers from 5 to 12 and counting each one in turn. The answer would be 8. Simple counting problem. More generally, if m and n are integers and m is less than or equal to n, how many integers are there from m through n? To answer this question, note that n equals m plus n minus m, where n minus m is greater than or equal to 0. Note also that the element m plus 0 is the first element of the list. The element m plus 1 is the second element, and so on. In general, the element m plus 1 is the L plus 1 element of the list. So the number of elements in the list are n minus m plus 1. So because the counting from m to n is inclusive, you would have to add 1 to the number of elements in the list. How many 3-digit integers are divisible by 5? What is the probability that a randomly chosen 3-digit integer is divisible by 5? Well, let's look at these in detail. Imagine writing the 3-digit numbers in a row, noting those that are multiples of 5 and drawing arrows between each integer and its corresponding multiple of 5. From the sketch, it's clear that there are as many 3-digit integers that are multiples of 5 as there are integers from 20 to 199 inclusive. So, by theorem 911, there are what? $180 such integers. Hence, there are 180 3-digit integers that are divisible by 5. By theorem 911, the total number of integers from 100 to 999 is 900. By part A, 180 of these are divisible by 5. Hence, the probability that a randomly chosen 3-digit integer is divisible by 5 is 1 over 5, or 0.2. Analysis of many computer algorithms requires skill at counting the elements of a one-dimensional array. Let A be a one-dimensional array where n is a positive integer, and the array goes from A1 to AN. Suppose the array is cut in the middle at value A sub m, so that 2 subarrays are formed. How many elements does each subarray have? Well, what is the probability that a randomly chosen element of the array has an even subscript, if n is even and if n is odd? Well, the array for A, the array has the same number of elements as the list of integers from 1 to m. So by theory 911, it has m elements. The array has the same number of elements as the list of integers from m plus 1 through n in the array 2. So by theorem 911, it has n minus m elements. If n is even, each even subscript starting with 2 and ending with n can be matched up with an integer from 1 to n minus 2, or n divided by 2. So there are n over 2 array elements with even subscripts. Since the entire array has n elements, the probability that a randomly chosen element has an even subscript is 1 over 2. If n is odd, then the greatest even subscript of the array is n minus 1. So there are as many even subscripts as between 1 and n as there are from 2 through n minus 1. Then the reasoning can be used to conclude that there are n minus 1 over 2 array elements with even subscripts. Since the entire array has n elements, the probability that a randomly chosen element has an even subscript is n minus 1 over 2n. Observe that as n gets larger and larger, this probability gets closer and closer to 1/2. So note that the answers to 1 and 2 can be combined using floor notation. For any integer n/2 floored is n/2 if n is even, and n-1/2 if n is odd. From back in chapter 4, by theorem 462, the number of array elements with even subscripts is the floor of n/2. So that the probability that a randomly chosen element has an even subscript is the floor of n/2 over n. And that will just about wrap it up for probability. We will get more into counting in the next, there's 9 sections, so 8 more, so the next 4 class sessions. We'll get more into counting and that sort of thing. I brought up in passing when talking about counting how the number of combinations of hash brown combinations at Waffle House is an exceedingly large number. I'm going to see if I can find out what that number is they have posted on the wall at Waffle House when they say there's so many combinations of hash browns you can have with the toppings available, and we'll work on that as a little side problem, how many there really are. And like I said, when I figured it out when I was an undergrad, it was larger than the number that they had posted on the wall. But anyway, just the one section for today. Light day for you. Have a wonderful day.